Okay, so obviously you're all here because you're watching the YouTube video anyway. What's my YouTube channel? Mr. Kyle Holloway, or you can type at Raider Math. Either one of them will work. So in 1.1, we're going to make sure that we all have the same common language and stuff, things that you might have forgotten over, the last several years. But we are going to be looking at key features of functions. Okay, that's what we're looking at. Now, when we talk about a function, what I think of personally, I think of a machine where we put in a singular input. We call that the x value typically, and we get a singular output or a y value out of it. If we have something that I put in one value and it gives me two different things, we don't have a function. So to start looking at these, we're just going to make a few crazy graphs. So I'm just going to do first quadrant stuff, but I'm going to make the same thing. We're going to draw like 3 different shapes here. And really the different types of shapes don't super matter, other than I want to make sure that we can have enough to compare and see something different. Do you guys, it's a little late to ask you now, but we'll go ahead and just pass these to each table. If you guys want graph paper and stuff, you're welcome to use it. They're all going on the ground. Okay, so we're going to try to draw some crazy graphs and just think about what they are. I need one type of graph or function. By name, you can tell me. Any type of function or graph that you remember seeing. So it could be a negative graph. What do you mean by negative graph? So it's going downward. So are you thinking of a line? Are you thinking of a curve? A line. Okay, what would we call a function that's just a straight line? Linear. Okay, so we'll go ahead and just sketch a nice linear function, and maybe it's something like this. And whether it's going up or down, it doesn't matter. Every single x value that I pick on this gives me one singular y value. And what I mean by that is if I pick this x right here, it only corresponds to one single y value on the graph. Is there anywhere that if I pick an x value, it gives me 2 or more y values to choose from? No, this is a nice linear function. Now, the easy way to check that is what's called the vertical line test. We'll talk more about that moving forward, but if you can run a vertical line through and you only cross the graph one time, then you have a nice function. Okay, that's a linear function that we have on the board. Other types. You can show me with your hands, with your words. Give me another shape of a graph that you guys have seen. All right, let's pretend I'm going to rob you, okay? I'm going to say, put your something. Hey, so he puts his hands up. And he didn't do it exactly like this, but I did. What are we doing? It's a parabola. It looks like a U, absolutely, but we have a parabola. So it doesn't matter whether a parabola is smiling, frowning, whatever the case might be. This is a nice linear function. We also have functions that exist that might be more like this. Okay, on this graph, and I wouldn't draw this if I were you guys because you don't have the ability to do all the editing stuff. But if I were to take a vertical line on this one, is there any place on this second graph, the blue graph, that I would hit it more than one time? If I have a vertical line? No. So is this a function? Yeah, this is a function as well. Now, we don't have enough time to draw out every possible type of function that exists because there's literally infinitely many of them. But can somebody give me one more type of function that we can look at? We might have seen it in our bell ringer today. Carson gave me the answer, and Rogue gave me the answer, and they're absolutely going to kill it. Absolute value. Okay, when we look at absolute values, just a different flavor of function here, they are always going to show up, for us anyway, in that nice V shape. Doesn't matter whether they open upward or downward, and if we don't get to see both sides of it the same, it might kind of look like it's not symmetrical. Is that a V shape, even though it's upside down? Yeah. Do you think that if we let that left side of it keep going, we would see that it's symmetric and it looks more like a V than it does currently? For sure. All of these things are functions that we get to deal with. Now, in these functions, we have a few different pieces that we're going to have to recall and a little bit of vocab coming up. As a reminder, how do we write vocab? How do I write vocab on the board? Do you guys remember? I use all caps with it. So we're going to be looking at these key features, and we're just going to say commonly discussed. or I'm going to say commonly important, rather, because there's a handful of them that we really care about, and we're going to try to blast this out over the next 10 or 15 minutes and then get you guys up on the board doing some stuff. Okay, so as we're looking at these things, we'll just make a couple comments. We'll define for ourselves at least a basic kind of intro, and I don't know why I'm looking at that board to write. That makes it weird. Let's define for ourselves, as simple as possible, a function. And I'm going to go underneath of it like this because I like that style more. Okay, for our purposes, I'm just going to think of it as one input, one output. That's the most important part of this. And we'll refine this as we go. We'll just say one input produces one output. Now, if your notes, like if they all fit on one line and you're writing it just like me, we can use some nice little arrows to give ourselves some more words. But if we're looking at one input and one output, all I think about with that is 1x, or input, 1x, 1y. If we wanted to be wordier, and if you want to be wordier, we could simply say vertical line test. Like that's where I want your head to go when we're thinking about, is something a function? That vertical line test, every time. Does it touch more than once? Can anybody tell me how to draw a function, or could you draw a function that's not a, can you draw a graph that's not a function, rather? We're gonna try it. In your margin, we'll pause this for just a second. These are functions. Do one more graph next to it that's not a function. And while you're doing that, I'm just gonna organize it here so we can see it. These are functions. I'm just gonna say func. And what I want you guys to do is draw a graph next to these in your notes that's not a function. And I'm just gonna come around and glance at them. Some graph that doesn't work with those rules. One input, one output. I think so too. Good choice. I think we're gonna get some other ones. If you're wrong, it's okay. I just want to stress that. But I want you to try to draw something where 1x gives you more than 1y. Okay, and as I see them, I'm going to put them up on the board here, and I'll just do them in a bunch of different colors. The first one that I saw was Carson's, and this is what he drew. That pink or purple, whatever color that is, line. Okay, why is that not a function? Goodness. Yeah, if we pick this x value, and I always use the x-axis to find it, this x value right here, how many different y values does it spit out? Infinitely many. And is that more than one? That breaks our rule. Does anybody have a graph that's different than this one? Who said it? All right. So as a different color, and we'll just put a few of them up here. You guys can pick and choose which ones you want. Mr. Nelson had something like this drawn. That's a parabola. What's different about this, though? So it might not really touch the y-axis. You're right. Maybe it does. I can't really tell for sure. Why is that not a function? Say that again. So I don't need it to intersect, but I like that idea. What's the single rule? For any x I pick, like let's say we'll pick this x this time, how many times does this x value hit this function? Twice. There's that x, it hits at that y value right there, and it hits again right there. For that one x value, how many different values did it spit out at me? 2. Is that allowed to be a function? No, it fails that vertical line test. That's the easiest way to phrase that. Okay, you could draw a circle, a heart. You could draw a S. Doesn't matter. Any of these graphs where if you were to pass a vertical line through it, it hits more than once, you do not have a function. Okay, so a little bit more specific vocab with these things. If we want to talk about the values that go into a function, there's 2 words that people struggle with, which this year we're not going to, because we're just going to think about it graphically to start, and it's going to make it so much easier. We have 2 special words, domain and range. Do you guys recall hearing those in algebra? Do you recall what they are from algebra? Anybody help? The X and Y, and there's some more words waiting here. Love it. the x values that we input, any x value that we can pick that will show up on that graph, we're going to call our domain. So check it out. If we just want to make this as simple as possible, which I would prefer, if we talk about all the inputs, we get what is known as the domain. Now, when we write this, we're going to learn some notation just to try to make things a little bit shorter in the long run. We're going to say that this domain is a vocab, so I'll do the same, sorry. The collection. And if you don't want to use the collection, you can use the set rather. Either one works. The set of all x values of a function that work. I'm going to put that in quotations. The set of all of the x values that work for our function. Now, this one's a little bit strange. We can only use one of these graphs. If we only looked at half of that sideways parabola, and don't erase yours, but I'm going to erase a little part of it just so we can see if we can make it a function. I'm going to start erasing along this line, and everybody, anybody, whenever I get to a point of erasing where I can stop because I now have a function, I want you to shout it out. So if I start erasing this, is it a function yet? Okay, tell me when to stop when we have a function on the board. Okay, so roughly there. Now you guys don't have to change yours, but if we ask about that function specifically, what x value would you estimate that it starts at? At this point, at the very start of my graph, the y-intercept, it would appear, what x value are we at? 0. So if I try to plug in -2 into this function, does it work? So would -2 be in the domain? Is it an x value that I can plug in? So we'll get there eventually, but on this one, definitely not. There's nowhere that this graph would ever use this point. So we would say that it's not in the domain. What is the domain of that red one that we have? It starts at 0. How far to the right does it go, where we can keep picking bigger and bigger x values? Infinitely far. So we've just listed the domain from a graph. We start at 0 on this graph, and we just work to the right forever and ever. What about the domain of that first line? How far to the left do the x values go that we can plug into it? Like, the board only goes to here, right? This is all I can see. But that arrow keeps going. If I could somehow, and I'm going to make you guys look over here because I keep making you guys turn. If I let this extend out and we just imagine that this line kept going, I got to this x value. Could I go down far enough to find a spot where I touch the function? For sure. So how far left could we go to start? -infinity. Okay, so we start at -infinity. We start working to the right. Do I touch it once I get to 1 and 5? And I don't see it, but if I went over to 200, would I still touch that function if I went straight up from that x value? Yeah, so we went from -infinity, furthest left, how far to the right? Infinity. Well, gosh, that's like all the numbers. Is there an easier way to talk about that? All this type of numbers. There's a fancy letter we use for it. Say it? Ooh, all reals, and we'll review that. Okay, so all the x values that work are the domain. What do we call the output then? We made eye contact, Henning. What you got? There's only one more word. We said domain. Do you remember the other one? The range. So if we try to use similar vocab stuff here, if the domain is the set of all x values of a function that work, how do we define the range? It can't be the x values. The y values. So we'll say that the range is the set of all y values, and I'm just going to say all instead of the set of all y values that the function produces, right? And we can either say that are produced, and I like to use the language that it spits out, I don't know why, but all y values produced by a function. Okay, so a quick check here. Let's look at, I'm going to add a number to this parabola that we graphed on that second one. And Sophia, I don't care what the number is as long as it's, what y value is this? It's below the curve. Is it negative or positive, do you think? Love it. Negative what? And I like -2, perfect. If we say that that was -2 as a y value for this function right here, I want you to turn to your neighbor, rock, paper, scissors, and again, I'm going to play with you. Whoever wins gets to decide, are you going to say the domain of that parabola right here? or is it your neighbor? So what are you going to pick? Yeah. Okay. Oh, whoa, we're different. You go 1, 2, 3, shoot? Okay. All right. I want you to speak. What, for that parabola, what y values get used? So, yeah, so like when we think about the y values, just in case you're getting goofed up on this, and I'll do this on the screen, if you're thinking about the y values of a function, or more specifically, we might just say the value of the function, right here, can we agree that maybe it's at like positive 10 on the y value? As I go along the graph of this function, it's now like maybe a 4. Do we agree with that? And what I mean by that is if we look at this point right here, whatever x value it is, who cares? The y value is like a 4 because we're talking range. How low does this function go at its very smallest? -2. So -2 is the lowest value it ever goes to. How high up does it go? So when we say from -2 to infinity, we just said the what of this function? Say it again. The range. Love it. That is the range of this function. So it's all y values that are produced. Does this all ring a bell? Okay. Cool. So last little thing, then we'll get up to the board and do a little bit of work here. Okay, we need some notation, and I'm going to change colors on this guy. Notation feels green to me. Okay, notation. When we are talking about these things, we are going to use one of two forms to write our answer. And I know which one I lied. We're going to use one right now. We're going to talk about what's known as set builder notation. Set builder notation. So it's already notation. I'm just going to call it set builder. Now, this vocab is going to be a little bit different because I can't just give you the nice definition. We're going to look at a quick example of this. So we have three choices from above. We had a linear function, we had a quadratic, and we had absolute value. Should we do the same types of functions, or you want to try a different one? Let's try a different one. Good choice. So really quick on this, we'll just graph, and you don't really need the graph paper here. We're not putting numbers. I mean, I'm going to put a number on it, but it's not going to be super specific. Let's say I have a graph that does this, and at 1, I get this point defined. And we're going to say, what y value is that, Gian? 5, deal. So there's a point on our function, and it does this. It goes up a little bit, and then down a little bit, like that. Now, good news is we only have one graph right now. Like, we're not getting too crazy. Let's call this function, just to be nice, we'll call it f of x. Not f times x, not f parentheses x. This is a function whose name is f, and the variable is x. That's what that notation is telling us. When we are talking about the domain and the range of these things, your book is going to use the full language. I suggest we use a little bit of shorthand for this. So if I'm talking about the domain of this function, I use DOM for the shorthand of that. The domain of, and I'm just going to use a bracket. What's that function called? Yeah, f, or f of x if you'd rather. We'll use f of x. That feels more natural. This is how I write the domain of f of x. And now we're going to get into our set builder stuff. So we're going to do this for the domain together, and then you guys are going to knock out the range on your own here. So when we're looking at this, the domain of f of x, when we are using set builder notation, we get to use our wonderful curly brackets. So these are going to be ugly on your page unless you practice, but we use these brackets. That curly bracket is what tells us that we are working with a set, a whole bunch of stuff. Now, remind me real quick, the domain, was that, oh, go ahead. Question? I was talking about how it's curly bracket. You did yours well? Nice. Cool. Okay, the domain is all the x's or all the y's? X's. And if you think you're going to get those goofed up, it's alphabetical. Domain and range, D and R, X and Y, they're both alphabetical. That's how I keep them straight. So we say it's the set, and that's indicated here, of all x values. And then we use a bar and we'll annotate this such that is this bar. And we'll write this out in words. What is true about the x values of this function? What's the first x value that we use, the smallest? 1. Do we actually use it like it's a closed point, or is it an open circle that we never quite touch? It's closed, so we do include it. How far to the right does it go? Infinitely far. So we don't have to write all infinitely many numbers. That'd be awful. But what we can do is make that easy. We'll say it's the domain of this function is a set of all the x values such that x must be greater than or equal to, because it touches right here at this x value. What value is it always greater than or equal to? 1. We have our domain stated. Now, language-wise, if you want to write down how to say this, you can, but this is totally optional. This is read, the set of all x, and I'm going to do it above so it fits nicely. The set of all x such that, and I'm going to underline that and go to that vertical bar because that's what that is telling us right there. This is all x values such that x is bigger than 1. That's it. Now, we can get some weirder examples, and we certainly will. But before we do that, I want you guys to go ahead and spend like 10 seconds. Okay, it's probably like 30. Talk out with your neighbor. I want us to get the range of this function as well. So we'll pause this here. What do you think I'm going to use for the shorthand for range? Ran, for sure. The ran, or range, and I'm always going to be specific of this function f of x. And it's the set of something. And I'm going to give you guys a moment. Talk it out. Write something down. But if you're not confident, I would just write it kind of light. I need to submit your attendance because I forgot to do that. What are you thinking? Can you find me on this graph the smallest y value? So I like that you're thinking these. These are the y values here, right? And these are the x values. So if I were to drag along this function, you tell me when I'm at the lowest point. So right here, and what is that y value? Say it again. So I like that you see 3 because you're estimating it, but I think you just might have given me the x. What about the y value? Where on this vertical bar am I at this point? So let me grab a different thing so the pointing's not as weird. If you guys want straight edges, by the way, they're in this basket up here. And I'll leave this one here with you. So like when I'm pointing at it, I'm only thinking about this y value. Like all these are the same y. Mm-hmm. Okay. When I get to the lowest point, what y value am I at? X. So, because yx. Yx? Like, how come you said x? Is what, like, can you explain that to me? Okay. And like, if we were to put numbers, if that's 5, what is this, do you think? Yeah. Good. So, what's the smallest y value? Yeah. Boom, you got it. So, smallest y value, what do we got? This is the set of all what values, I guess. Because we need, we'll say that again. For the range, are we talking about the x values or the y values? The y values. So, little change there. This is the set of all y such that, what's true, Carson? Y will always be greater than or equal to 1. So, he says greater than or equal to 1. I liked it in the first half. Yash, when I'm looking at this function, I'm just going to drag my finger along it. Tell me when I'm at the lowest point of this function. And I'm not flipping you off. I just point with that finger. Okay, right here. What is the y value here? Love it. So, Carson, do we get below 1? Do we, if I follow this function, do I get lower than a y value of 1? Well, if we were to make this point, it looks like it's roughly 2 comma what? Is that smaller than 1? So what do you think we should say? Y is greater than or equal to? 0. Love it. Okay. Domains and ranges from graphs, piece of cake. Nothing crazy about it. Did you guys bring your calculators today? Okay. Do you know how to use your yellow calculators? Okay. So do you want an example in your notes, or do you want to go do an example at the board? Notes? Okay. So a quick example. and we'll probably have A and B. You guys are cool to use your calculators. I want you to find domain, and I'm just going to shorthand it DOM, and the range of, and then we'll do a couple of these. Okay, we're going crazy with it. The first one we're going to say is the function y equals 6x minus 2x squared. Now, you can use your calculators to do this. It is not required on this problem. This is not a super nice one. But domain and range of this guy. And then on B, while you guys are talking about that in your small groups, I would use the calculators. I think it'll be helpful. But I'm also going to give you a graph instead of just the equation. So we'll give you guys a second. I want to hear you talking it out. If you don't know the answer, are there other people in class who might? For sure. Don't just all flood one person, but talk it out. I want to hear it talking. All right, so a little bit more discussion to be cool. If you don't know how to use your calculator, now would be a great time to say, Holloway, I thought I did, but turns out I really don't know how to do this on the calculator. All right. So if you're struggling, do you think it's easier from the equation or from the graph? Anybody have an opinion on that? Probably from the graph. So if we wanted to graph a function on this calculator, how on earth do we do that? Where do you get that? Like, where on my calculator would I push it? Top left. You will see a button that says y equals. And we'll go ahead and pull this up here. Okay, so here's my calculator. We're going to try to fight the glare, but it's always a battle. Oh, it's actually not bad today. Okay, up top, we have this lovely y equals button. There it is. What is the equation that I just gave you guys? 6x minus 2x squared. So some little tips and tricks that if you're not super familiar with these might be helpful. How do I get x to show up in my calculator? So you can use alpha start to get the letters, or there's a button right next to alpha that has x, t, theta, and looks like nu. If you hit that, it gives us an x. 6x, and what was the other part? Oh, I need to back up. Okay, very top left is y equals. And then I'll open this, and then it's 6x, and it's minus 2x squared. How do I get squared? So two options. These ones are nicer than the other ones you guys used. You can use the caret. That's okay. Or because squared functions or quadratics are so common, there's a button right here on the very left that says x squared. You can just hit that. Okay. So I now have this stored in my calculator at y1. That did not help me. What do? We got to graph it. Now, I did not reset all your calculators. So all of our graphs might look a little different, but we'll clean that up. Graph this to graph this, or whatever functions we have, it's on the very top right. I'm going to hit that. This is what my graph looks like. Now, I'm going to steal this real quick, and I'm just going to do something crazy, okay? Okay, this is not what Guillen's look like for real, but this is, I changed something on it because our calculators might be set up different. This is the same function, graphed differently. Can you guys tell? No, these obviously don't look the same, but I'll tell you, if we go here, they are the same. I can see they're the exact same. Why on earth would they look so wildly different when I go to graph these? Say it again. The settings, the way that we've made our scale look. The easiest way, if you're struggling, if you get a graph and it looks something like this, we need to change how we're looking at stuff. The cool thing is that there's a button all the way up here, window, that we can pick these values if we want. Or what I would rather do than having to pick my own X's and Y's is one button to the right. There's this lovely zoom button. If you hit zoom, what's it say on number 6? Standard. You can either scroll down and hit enter, or you can just simply type the number next to it. If we go to standard, it sets me on that -10 to 10 in both directions. Now we have the exact same graph. From this graph, we can see pretty well where the max is. We all agree it's right here. Yeah. Anybody know exactly what y value that is? Okay. I forgot we had Friday schedule. There's no homework this weekend. Peace out.